While designing our own convolutional neural network architectures can be a lot of fun, it's also a very time-consuming project. In fact, researchers had spent thousands of hours to design well-performing CNNs, and it's actually efficient to just reuse these existing architectures. So in this video and in the upcoming videos, we will discuss the main ideas behind these architectures and see how we can leverage them for our own projects. So first, let's recap the main ideas behind CNNs. So one of the key ideas behind CNNs is a sparse connectivity. So in fully connected networks, every unit in one layer is connected to all the units in the next layer. However, in a CNN, a single element in the feature map is connected to only a small patch of pixels. So we have sparse connectivity as opposed to full connectivity when we use convolutional neural networks. Another key idea behind CNNs is that we have weight sharing or parameter sharing. So that means that we are sharing the same weights for different patches in the input image. And another main idea behind CNNs is that we have many layers. So using many layers allows us to combine these locally extracted patterns to form global patterns for the multilayer perceptron unit at the end, which does the classification. So the rationale behind this sparse connectivity is that we are assuming that neighboring pixels are related. So for example, assume we are trying to classify a cat or a dog. So if we zoom into the eye region of the cat, all the pixels in this region form the eye, and so the neighboring pixels are related in fact. And the rationale behind this parameter or weight sharing is that we assume that the same filters that we apply work in different parts of the image. So if a filter works well in one part of the image, we also assume that it would work well in another part of the image. So the sparse connectivity and the parameter sharing are assumptions we make. Or in other words, we can also think of them as restrictions. So we call these assumptions and restrictions inductive biases. So using these assumptions or inductive biases, we actually reduce the training data that is required. In fact, a fully connected network could also learn, for example, that neighboring pixels are related, but it would need way more data in order to figure this out. Now, a nice side effect of these inductive biases is that convolutional layers are actually pretty small compared to fully connected layers. So convolutional networks are actually way more resource efficient than fully connected multilayer perceptrons. So let's illustrate this aspect with an example. So here I'm showing you a fully connected multilayer perceptron with 3 hidden layers and 1 output layer. And here assume we are working with a 224 × 224 input image with 3 color channels. So if we have 3 color channels and 224 × 224 pixels, that's an input feature vector of 3 × 224 × 224. Then if we have 10,000 output nodes in the next hidden layer, we multiply that number by 10,000 and we add the 10,000 bias units to it to compute the total number of parameters of this layer. So you can see here for this fully connected network, the first layer already has 1.5 billion parameters. Now let's assume the second and the third hidden layer are a little bit smaller, where for the second hidden layer we have 10 million parameters. For the third hidden layer we have 100,000 parameters. And for the output layer, we have 1000 parameters. So in total here, we have a multilayer perceptron architecture with 1.5 billion parameters. And this is a multilayer perceptron to classify 224 × 224 color images. So now if we look at the memory footprints, that would be 5 gigabytes of weights that we have to store here. Now in contrast, if we would develop a convolutional architecture for 224 × 224 color images, the size of this convolutional network would be just 1.5 million parameters. So that's 1,000 times fewer parameters compared to the fully connected network. So to illustrate how we compute the size of a convolutional layer, let's take a look at the first convolutional layer here. We have an input image of 3 color channels, and we use a kernel size of 5. So that's already 3 × 5 × 5 weights. Now if we have 8 output channels, we multiply that number by 8 and add the 8 bias units. So that's 3 × 5 × 5 × 8 plus 8, which is 608. So you can see 608 is way smaller than the 1.5 billion that we had for the first hidden layer in the multilayer perceptron. And so instead of having a 5 gigabyte large network here, in total, this network has a size of 0.016 gigabytes, which is just 160 megabytes. Okay, so in this video, we talked about the motivation and the assumptions behind convolutional neural network architectures. In the next video, we will talk about CNNs and their inceptions. And by the way, this is a pun that will make more sense after watching the next video.